Okay, let's go ahead and look at these couple of problems here. So I'm just going to open the video that I've downloaded, and so this will be kind of a video in a video, and I'll just sort of sit here and watch it with you and make a comment if I need to, but just write down the solution as we do it here and see if you can start to, again, sort of incorporate the strategy that we're talking about into your everyday practice here. So go ahead and watch this video. Okay, so this is a clip for the first problem in the 1-3. Actually, it's probably best to watch it in theater mode. Discussion. So we've got a problem where a car accelerates on a straight road from rest to 75 kilometers per hour in 5.0 seconds. What is the magnitude of its average acceleration? Okay, so we're going to follow our standard procedure. We're going to start with our frame of reference or our motion diagram, and we're going to collect the information, and then we're going to figure out what formula we need and then solve it. Okay, so there's our standard frame of reference with an origin and the positive x values, and we're told that we go from rest to 75 kilometers per hour, and so we're free to say that our initial position is 0 meters. We're not given any information about how far we do end up going. Okay, we could figure that out if we wanted to, but we're not asked to. And then we are told that we start from rest, so our initial velocity is 0 meters per second. Then we're told that our final velocity is 75 kilometers per hour. Now we have a little problem here in that for most of our problems we need our velocities and our displacements and accelerations in meters rather than kilometers, and meters per second rather than per hour. And so we have a trick. Let me just show you why this trick works. So let's say we have 75 kilometers per hour, and we want to change that into meters per second. Okay, so my strategy for these is that I start with one value, I start with one unit, and I say I want to get rid of this unit. What do I want to change it to? Okay, and so usually I can do this in one conversion. I want to get rid of kilometers, so in order to be able to get rid of kilometers, I put it on the opposite side of the dividing line, and that way it'll cancel out, right? Kilometers cancels kilometers. And then I want to add in the unit I want to create. I want to create meters, and I know I have a conversion between meters and kilometers. So I can say 1 kilometer is 1,000 meters. Okay, and then I want to get rid of hours, so I'm going to put hours on top here, so that'll cancel out. So I just put it on the opposite side, and then on the other side I want the unit that I want, so I'm going to put in seconds. Okay, that's what I want to create, and so now I'm going to say 1 hour is 3,600 seconds. Okay, so really, in order to get from kilometers per hour to meters per second, all I'm really doing is dividing by 3.6. 1,000 divided by 3,600 is dividing by 3.6. So if I want to go from kilometers per hour to meters per second, I divide by 3.6. And I can reverse this process if I want to go from meters per second to kilometers per hour. I just do the opposite, and I'm going to multiply by 3.6. So this is our standard trick. Okay, commit that to memory. Now, I want to change velocity from kilometers per hour to meters per second. So I will just divide by 3.6, and that gives me 20.8 meters per second. Okay, so I go from 0 to 20.8 kilometers or meters per second in whatever time it is that this is going to take me. And then I need to put in my acceleration. I know acceleration is going to be in the positive direction because my arrows for velocity are increasing in length in the positive direction as well. So I'm going to say A equals, but I don't know what it equals because that's what I need to find, right? So given x0 equals 0 meters, I don't know what x is, v0 equals 0 meters per second, v equals 20.8 meters per second, and then I need A, and my formula is just going to be my standard acceleration formula. I've got v and v0, so I can say A equals delta v over t equals v final, my final velocity, minus my initial velocity over time, and I know my initial velocity is going to drop out. Let me get rid of this stuff here. We don't need that. And then I'm going to solve. All I need to do is plug my values in and solve. And so A equals, and V is 20.8 meters per second. And I'm going to divide by the time. Oh, I forgot to put time in my given, 5.0 seconds, divided by 5 seconds, and that equals 4.2 meters per second squared. Okay, so that's the answer to this problem. Go ahead and go to the next one. Okay, so that was the first problem. Hopefully, and here's a, if you want to just see the picture of it at some point in the future, here's the actual solution there. I screwed up a little bit. I forgot to put my units in here for 5 seconds. I apologize for that. That's naughty of me. So let's work on the second problem again, or now, and let's see how that one goes. Okay, so this is the second problem then in the acceleration 1-3 discussion. An automobile is moving to the right along a straight highway, which we choose to be the positive x-axis. The driver then steps on the brakes. If the initial velocity is v0 equals 15 meters per second, and it takes 5 seconds to slow down to a stop, what was the car's average acceleration? Okay, a couple of points. We need to begin to make sure that we understand the idea that in physics, the word acceleration does not necessarily mean that the car is speeding up. Acceleration simply means that the motion is changing. It could be slowing down as well. It's just acceleration is just a term that means change of motion. Okay. Now, in more modern times, obviously, it's come to mean speeding up. But in physics, it doesn't have to be. It could be slowing down as well. But we also give a special term to the motion of slowing down, and that is called deceleration. And we'll find out that we're going to have to make a distinction between that and negative acceleration. Negative acceleration is not the same thing as deceleration. Negative acceleration is acceleration that is in the negative direction. Okay, so we'll work all of this out as we go through some of these next few problems here. But let's work our way through this one then and see what we mean by what we're talking about so far. Okay, so an automobile is moving to the right along a straight highway which we choose to be the positive x-axis. So always, always, always we're going to start our problems with our motion diagram. Oops, let's make it bigger there. And my positive x directions and my origin. Okay, and as always, we collect the same information in the exact same way every time. My initial position here is going to be 0 meters. We haven't been told otherwise, so we're free to make our statement that the initial position here is 0 meters. We are not told what the final distance is or what the final position is, so we can put a question mark there. That's a pathetic question mark, isn't it? So do that. Let's change that. Okay, that's not much better, is it? Okay, we're told that our initial velocity when the driver hits his brakes, V0 equals 15.0 meters per second. And we know that when we come to a stop, our velocity is 0. So our final velocity is 0 meters per second. Okay, now be aware that what we're doing with our velocity is this. Okay, so we add in our velocity vectors so we can see our motion, what the motion is represented by here. And now we need to ask the question, if the acceleration of this was in the positive direction, that would mean that the automobile would actually be speeding up. So we need to add in an acceleration that's going to cause the car to slow down. And so what we're going to say is that the acceleration here is in a negative direction. Now the car is certainly decelerating, it's slowing down. At the same time, it's undergoing negative acceleration. Okay, and we want to find out what that negative acceleration is. So because our acceleration arrow needs to be pointing in the negative direction here, to indicate that we're going to oppose the motion of the car. Okay, and that's another good way to think about it. Acceleration causing deceleration needs to oppose the motion of the car. And another thing that we can say is that the acceleration arrow always has to be going in the direction of increasing lengths of velocity vectors. Okay, so even though the velocity vectors are pointing to the right, the motion is to the right or the positive, the length of these vectors is getting longer going to the left. And it's always going to work out that if I make my acceleration arrow go in the same direction that the velocity arrows are increasing in length, I will always have the correct direction for my acceleration. Okay, so a lot of things to consider here. Okay, so we need to finish this problem then, but we're actually going to have to move it to the next video, the final solution for this. And so go ahead and close this video and open up the next one. Okay.